So let us continue with our series. So today we will discuss rank of matrix, invariant subspace. Basically, we will just start invariant subspaces and introduce eigenvalues and eigenvectors here. Last time we have the dual space. So the dual space is just defined this way. Some people write it with this notation. Here we will write it with the apostrophe here. This is just a set of linear functionals. So linear functionals are just linear maps from V to the scalar field F. And then we also have we just call this the dual space of our space vector space V. We also introduced the notion, or we have discussed the notion of a dual map. A dual map of T, which is an element of LV to W. So its dual map is T as T prime. It is just the map from the dual space of W to the dual space of V. And then we define what it means. And then we go through theorems on the null space of our T prime and its range space, or the range of T prime, with respect to the null of the original map T and the range of the original map T. And also we get the matrix of dual map T is just, which is denoted as M T is just equal to the matrix of T, get the transpose. So that's our, we also have the definition of annihilator. So annihilator is just a subspace of V prime, or a subspace of the dual space of V. So these are the set of linear functionals, even which if we evaluate this to any elements of our subset U, we get 0. So we also have the annihilator of U. So today we will start with the rank of matrix. Okay. So what's the rank of a matrix? We have, before going to the rank of the matrix, we will define first what we call the row rank and then the column rank. Here A is a M by N matrix with entries from our scalar field F. And then define the row rank. This is just the dimension of the span of rows of A in the F1N. So this is just the matrix, which is just one row. And then we get the column rank of A. This is just the dimension of the span of the columns of A in F. Here we have M1. So this is just our matrix of um, one one column, and then there are many many columns and um, many rows and one column. Okay, let us give an example. So we get a matrix with 4, 7, 1, 8, and then 3, 5, 2, 9. The span our our rows is the span of 4, 7, 1, 8, and then 3, 5, no comma, 3, 5, 2, 9. So in F1, 4. 1 here means only one only one row, and there are 4 columns. So look at the vectors above. Neither of v1 and v2, because consider this, v1, v2 are scalar multiples of the other. The span of this list is as dimension 2. So the dimension of row space, the dimension of the span of rows, or let's say the column rank, the row rank of our A is 2. Now observe that if you get the span of the columns for 3, 7, 5, 1, 2, and 8, 9, we have observed that neither of the two vectors is a scalar multiple of the other. So the length has dimension. If you look at the first two vectors, these and these are not scalar multiples of the other. So so that the dimension of the span of the list has high dimension at least 2. This is in F 2, 1. However, this one, the span is the span of this has at least 2. However, the dimension of our F21 is just 2. Thus, this will give us that the span of this is equal to 2 also. That means that the column rank is also 2. Notice that we have the same row rank and column rank here. This is actually a result that the dimension of the range of T is equal to the column rank of MT. So let us state that properly. So get V to W, we get a map from V to W here. Then the matrix, let us consider the dimension of the range of our T is equal to the column rank of our matrix of the linear map P. So these are vector spaces. Of course, our setting is finite dimensional vector spaces. That is we can just have finite elements in the basis of V. Suppose we get, okay, let's start the proof. Get V1 to Vn and W1 to Wm. This is basis of V. This is basis of W. Okay? So, um, if we just verify that the span of TV1 up to TVn is equal to the span of MTV1 V1, the matrix of this map up to M of TVn. So I think you can verify this. Therefore, this one means that the dimension of the span, let's consider this as let's say this is x, the span of x here is equal to the, let's consider this as y, the span of y. That means that however the dimension of this is equal to the dimension, or this is equal to the column rank. And this means that the range of T, which is just the span, means that the range of our linear map T given by the span of X, here is our X here, is just equal to, so because they are of the same dimension, so this is the same, the dimension of the span of X, is equal to the column rank of our matrix of the linear map T as desired. Now, this is the theorem that is given in the example. If we get a matrix, A has the same column rank and row rank. Okay, so how do we prove this? So let us consider a map, linear map from Fn1 to Fm1. So here, this is T gets an element X here and then maps it to A times X. Okay. Your M of T here is just equal to A, where with respect to, this is with respect to standard basis. Actually, you can use other bases. Now, compute the column rank. The column rank of our A is equal to the column rank of our matrix T. This is equal to dimension of the range of T, which is equal to the dimension of the range of our T prime, which is just the dual map of T. This is equal to the column rank of matrix of T prime, which is equal to the column rank of what is our matrix of T prime? This is just the column rank of matrix of T transpose. So matrix of T is A, and the matrix of T transpose is A transpose, which is just the row rank of our A. So the reasons I have stated while I write them, so that's it. Because we know that the column rank and the row rank are the same, we define the rank of matrix A in Fmn. So this is the set of matrices of interest with interest in F of row M rows and N columns is just the row column rank of our matrix A as we have stated earlier. So I think this finishes our chapter on um, on linear maps. Now, I will be skipping the chapter on polynomials, and I will just state the necessary results that we will use in the preceding chapters, and then maybe state them as needed. We will go directly to the discussion of invariant to chapter 5 of our book. So this is entitled eigenvalues, eigenvectors, and then we get invariant subspaces. So for the notation, F here is just C or R, and then V is vector space over F, finite dimensional, unless it's stated that it's not finite dimensional. So here we will study linear maps from vector space into itself. So we will just study operators here. So let us start the motivating example. So the first part is invariant subspaces. So recall that this LV is the set of linear operators from V to itself. And then if we look at to better understand what operators are, we can look at our, let's see how we can go. Suppose that our vector space B is a direct sum of U1, U2 up to UM, and then UJ is a proper subspace, meaning none of U1 here is equal to V. So we need to understand, so we want to understand the behavior of T restricted to U sub J, where this is the restriction of T to just our U sub J. So dealing with the T restricted to this subspace should be easier than dealing with T, because U sub J is a smaller vector space. However, if we intend to apply tools in the study of operators, there are, but sometimes if we get T here and then restrict it to U sub J, it may not be in U sub J. That's why we want to consider only your t restricted to u sub j, and then we get v here is just equal to u, wherein u is also in u sub j. So this is the notion that we want of an invariant subspace. So this has the name is very leading. This is called the invariant. So suppose we get a linear map to V, and then we get a U subspace. U is invariant under T if U in U here implies your transformation applied to U is also in U. In other words, T U is an operator on the subset U or subspace U here. I will state some common examples. We get 0, we get the V, and then we have null of our T, and for here we get range T. These are all invariant subspaces. So for example, reason for nullity, suppose that U is in the nullity, then T of U is also 0. Hence, your T of U is also in the null of T. So for the other, we did this one, and then this one, and these two, we just follow the same argument. So aside from V and this, are there other invariant subspaces? Okay, the answer is yes, but we will consider this later on. Null T and range T are invariant under T do not necessarily provide easy answers because sometimes the null is just the 0, the vector space containing 0, or and then the range may be equal to just the entire space V. So it doesn't give a lot of information at all. Now let us consider a concrete example. Suppose we get a linear map, an operator on the polynomial with coefficients in R, and then the operator is defined P is equal to P prime, and then P4 here, the polynomial of degree at least 4 is invariant under T. Why? Because if P is in P4R, P prime has degree at most 4. So you take the derivative of a polynomial, then for example, it's degree 4, then the derivative would have degree 3, or lower than 4. Now we will return to the study of invariant subspace in a more general sense later, but we will investigate the simplest possible non-trivial invariant subspace with dimension 1. So we now go to eigenvalues, eigenvectors. Here we will study simplest one-dimensional subspace. Of course, how do you define this? So if we get uh, a, a vector in the vector space V, of course, we don't want it to be zero. We want to define U as just the span of V. So this is just lambda V. In here, we get lambda in F, or this is just the span of the vector V. Of course, U is one-dimensional. Here, one-dimensional because it's just spanned by our vector U, vector V. All right. So, and every one-dimensional subspace of V is of the form for an appropriate choice of V. And if U is invariant under T, then T of V is in U also. T of U is also in U. Hence, there exists a scalar lambda such that your T of V is equal to lambda V. Conversely, if T of V is lambda V for some lambda in F, then the span of our V is a one-dimensional subspace of V invariant under our T here. Okay, look at this equation. T of V is equal to lambda V. So this is just intimately connected with one-dimensional invariant subspace, and this is important because this is very important. That is why we have names for this lambda, for this V here. Okay, let us name them. So T an operator on V, and lambda scalar is called an eigenvalue. Okay, some books refer to this as characteristic value. Eigen here means own value. Here is just the value in English. The eigen here is a German word. This is the eigenvalue of the operator T if there exists a vector V in V with V not equal to 0 and the operator applied to V is equal to lambda of V. All right. So let's consider some conditions. And we will say this as theorem. Number one, the following, a little abbreviate, the following are equivalent. Number one, lambda is an eigenvalue of T. Number two, T minus lambda I is not injective. Number three, T minus lambda I. Number four, T minus lambda I is not surjective. It's not bijective, or it's not invertible. For the proof here, 1 and 2 are easy. Okay. By definition, and the others are just conditions on 3 point. On the book, it refers to the injectivity is equivalent to surjectivity in finite dimensions. So it's easy. All right, here I is the identity operator or identity map. Now we will define others. Wait, follow from previous theorem. Okay, we will define the vector. We have t in here, and we have lambda in f. Eigenvalue of t. Your v in the vector space V is an eigenvector. Eigenvector corresponding to lambda if V is non-zero and T of V is lambda V. All right. All right. Let me state a remark here. T of V is equal to lambda V if and only if T minus lambda I of V is equal to 0. Here V is non-zero. V is eigenvector of T corresponding to lambda if and only if your V is in the null space of T minus lambda I. Okay. I think it's the statements that we have mentioned are abstract. Let me consider an example to illustrate what's going on. Let us consider an operator on L F2. F here be the complex number, and then T defined as TWZ is equal to negative ZW. So we must find the goal here is to find eigenvalues, eigenvectors of T. Solution, we get to find a lambda such that T of WZ is equal to lambda WZ. So here, here we get negative Z is equal to lambda W, and then W here is equal to lambda Z. This is from here and here. Okay, just equate these two. Now we will discard non-trivial solution. So if we're going to substitute Z, we get lambda. Here, this is our we get negative z here, and then is equal to lambda, and then w is lambda z. So we get negative z is equal to lambda squared z. Our z can't be 0. Otherwise w is 0. Don't want your z we don't want the 0, 0. So we need to have to simplify this so that we get other solution aside from the trivial one. So we get negative 1 is equal to lambda squared. That means we get lambda is either the negative number, the square root of negative 1, or lambda is equal to negative I. So we get two eigenvalues. Now for each eigenvalue, for lambda equal to I, we want to find the corresponding eigenvector. Okay? For the first one, we have if w and then for lambda equal to I, we get the vector of the form w and then negative wi as we have in here. And then for lambda equal to negative I, we get w and then wi eigenvector corresponding to I to negative I. Okay. Now we have a theorem on linear independence of eigenvectors. So we get D here, and then we get U1 to be M. We get a lambda 1 to lambda M. We have distinct eigenvalues of our T, and U1 to be M corresponding eigenvectors. Then what can you say? Your V1 and Vm are linearly independent. Okay, so I think we need to prove this. So how do we start the proof? We will just do the sketch of the proof. So the first thing is we get vk in the span of our v1 to v of k minus 1. So that k smallest. And then what can you say about vk? vk is just a1 v1 up to a k minus 1 v k minus 1. So if we apply t to both sides, t here and then apply t here, what we get is the following. Okay. We get the following. Lambda k, and then we get v sub k is equal to a1 lambda 1 v1 plus a k minus 1 lambda k minus 1 and then vk minus 1. All right. Then if we multiply both sides, so we have here, and if we multiply this with lambda k, so we get 0, this one, this part here, and here, with lambda k, we get 0 is equal to a1, and then we get lambda k minus lambda 1 v1 plus a k minus 1 lambda k minus 1 minus lambda k pala, lambda k minus lambda k minus 1. And then, since we chose k to be the smallest integer satisfying this statement, we have v1 to vk minus 1 linearly independent. It means that a1 to ak minus 1 is equal to zeros. Okay. However, this means that vk equal to 0. This means that vk is equal to 0, which is a contradiction. Contradiction to the hypothesis. Thus, your v1 to vm is linearly independent. Here we have, we assume that this is linearly dependent. So since this is linearly dependent, we can express let k be the smallest such that v sub k is in the span of the first k minus 1 vectors, and then applying our transformation, we get t of vk is just lambda k of vk. So you just apply this one and then you get this, and then multiplying this side with lambda sub k, and then subtracting this with this, we get this inequality, this equality, and then applying the linear independence of v1 to vk minus 1, we get the coefficients a here are 0. Therefore, this means that v sub k, this is all 0. So this means v sub k is always also 0, which is a contradiction because assumption is this is a contradiction to our hypothesis that vk is an eigenvector. Vk eigenvector. Okay. So yeah, you can redo that proof and then make sense of it if you want. And then we now go to the next theorem that says that the number of eigenvalues of t is at most equal to the dimension of the vector space V. So the proof here is just if we get lambda 1 to lambda m values of t and v1 to be the eigenvectors, then your v1 to vm is linearly independent, and thus, because this is linearly independent, m must be less than or equal to the dimension of v. Lambda 1, lambda m, eigenvalues, your dimension of v must be the upper bound for m. So this is a square sketch of our proof. Now we go to slightly, this is already seen as before, but let us how this restriction map and the quotient operators are related. Let us define them, and I will leave to you the verification that these operations or operators are well defined. So let me define a restriction operator. So here T is linear operator, and then U is invariant subspace of the vector space B under our linear map T. The first is the restriction map. I will name this operator this time. Actually, it's also a restriction map. T restricted to U is also a linear operator on U. It's defined as T restricted to U is equal to, no, let's define it as T is equal to T of U for all U in the subspace U, and then the quotient operator T mod U is an operator on the quotient space V mod U, defined as T mod U of our V plus U is equal to T of V plus our U. This is for all V in the vector space V. So look at the domains and range of the operators. So T here, a restriction map is just restricted to U instead of and to B, and then the other one is the quotient operator. So this quotient operator is well defined because if you get two affine subspace V plus U and W plus U, if they are equal, then T of V plus T U is equal to T of W plus U. Hence, your V minus W is in U because of the invariance of T. That means T of V minus W is also in U. And therefore, TV minus T of W is in U, which implies that our T of V plus U is equal to T of W plus U as desired. So I'm just reading here from the book, but I think I will leave this as an exercise uh, to, to think of these operators in terms of their domains. Now, the restriction map and the quotient map do not provide enough information about our linear map T. In the next example, we will illustrate that the restriction map and the quotient map is equal to zero or just zero, even though T is not the zero operator. All right. So let's consider the following example. And this is the end example. So define T from as a linear operator on F2, and then T of xy is just y0. And then consider a subspace U consisting of x and 0, where x here is in the scalar field. Number one, U is invariant under T, and T U is the zero operator on U. Here, note that T is not the zero, but T of U is the zero operator on U. Okay, let us show this one. So solution. X U is an element of U here. Thus, we get T of X U is just 0, 0, which is an element of U. Hence, U is invariant under T. And of course, T restricted to U is obviously the zero map or zero operator. So whatever you, since our X is arbitrary. Okay. And then the next example, C, T of T mod U is the zero operator on F squared mod U. So now we get an element of F squared, then T mod U of X, XY plus U is T of XY plus U, which is just, what is T of XY? T of XY is just Y0 plus U. Now, what? This is just 0 plus U. Since our Y0 is eaten by, or is absorbed by U, that means our T mod U is, or the quotient map is the zero operator on the quotient space of F2 modulo the subspace U here. Okay? The zero operator. Observe that T is not a zero operator, however, your T mod U, or the quotient map of T by U, and then the restriction map of T by U, they are the zero operator on the respective examples that we have considered here. All right. So I think that's enough for today. So for the next meeting, we will consider more on eigenvectors and your upper triangular matrices. So what are upper triangular matrices? So we get 0 here, and then the diagonal is, what's the upper triangular matrix? The diagonal is 1, then 0, then 0, okay, 0. Okay, I'm missing out some. So we get, for example, we get a 0, 0, 0, 1, 2, 3, 4, 5, 6. A sample of the upper triangular matrix that is only the upper triangle has elements. This one, and then I think we will just cover these upper triangular matrices and eigenvectors next meeting. So I think I will end here. Thank you.